Here? I don't know.
What's happening?
I got silence the second minute.
We're gonna go live in 30 seconds, so we're just trying to get some 30 seconds in. Right? What was the title?
Yeah, I'm just,
What was the title?
wasn't it different on the top?
Doesn't matter.
They have changed the title like
This was the title.
Yeah.
Don't worry. I know what you're saying. Just saying, don't worry enough. Too late.
Right, you're good. We're live.
We good? Okay. Also on YouTube? Okay. Awesome. Yeah, thank you so much for joining today. We're gonna have a sort of a special session. We have Aldo Perea today with us. And I think a lot of you already know Aldo done some amazing work in getting the libraries built around training and customization of language models. And what we're going to do today is, as we move into LLMs powering most of the agentic applications that we're seeing around, we all have come to a realization in the AI innovation, but also more broadly that, the path to having agentic employees will lead to an expectation that just like humans, as they work, as they learn on the job, they become better, that these agents, these virtual employees will also improve as they do the task more and more. Yeah. And if you map this back to the technology that would potentially empower it, you naturally will rediscover that, hey, people have been sort of thinking about this kind of problems in reinforcement learning, right? Where you have an agent operating in an environment. Typically, it used to be 10 years ago, some video game, we're thinking about OpenAI gym era. But we're kind of back again there, right? We have these agentic applications operating in an enterprise setting. And then if you extrapolate on this analogy, we're naturally going to find ourselves needing reinforcement learning. So what Aldo is going to do today is paint that picture a little bit for you, and then dive a bit deeper into the technical details of how today you can get started, what libraries are available, what are their features, things that he has put together the team actually built. So without any further ado, I'll hand it over to Aldo.
all right.
Awesome.
Okay, so hello everybody. So thank you for the introduction, Akash. I think you actually it feels like you actually read the presentation, even though I just finished it. But you were exactly on point. That's exactly what I'm going to do today. I'm going to talk to you about how reinforcement learning kind of plugs into the agentic systems era. And without further ado, I'm just going to start. So I'm going to start by just talking about what the AI revolution that happened when ChatGPT was released back in November in 2022 kind of meant for the world, and how that kind of has transformed into today's agentic systems. But before that, I want to mention several things that have been hyped by artificial intelligence over decades. So I'm going to start with IBM's Jeopardy win in 2011, which was a massive kind of win for artificial intelligence, but it was hyped quite a bit. We were saying that at the time that we were just basically creating a chatbot that could help doctors or lawyers, and that was actually not possible at the time. The methods were not generalizable enough. And then we also have a breakthrough in Go and with reinforcement learning to play games, and also Atari. It was also hyped up, meaning people were saying that we were going to apply reinforcement learning everywhere and then basically solve all problems of humanity. But it didn't happen, as we have seen so far. But then in 2022, ChatGPT happened. And myself, and I think a lot of people in the AI research community saw this differently. All of the methods that I was mentioning before, they were not generalizable because they required massive amounts of training in particular narrow domains, and they would not generalize across different tasks. But ChatGPT was different because the environment and the modality of ChatGPT was natural language itself. And if you think about it, like if humans go around in the world and kind of like just unroll themselves and manage to solve tasks in natural language and communicate with each other in natural language and basically do math in natural language, then maybe you could think that this was actual, like closer at least to artificial general intelligence. And at least but a lot of people kind of got super excited about it. I was working at the time in like neurosymbolic methods for learning, for embedding kind of intuition into models. But when I saw this, I was like, maybe I don't need to do all of that PhD, like super heavy stuff in symbolic methods, and I can just try to put all of that into data. And that's what I did. But anyway, what was ChatGPT? ChatGPT was a chatbot-like experience, user experience, in which you just kind of like talk to it, you ask questions, you give it context, and then it just gives you a reply. And that was amazing at the time. And then we could basically try to do almost anything in natural language, or could we? There was this kind of big headline problem in which I think Gemini was telling people that they should put glue on pizza, and they were trying so much to fix it, and they couldn't. They had to like actually just take down the robot for the AI for a little bit. But yeah, so these models hallucinate quite a bit, and they had a bunch of problems. And so basically, this kind of lead me to what was the solution at the time. How do you mitigate some of the problems that a normal language model would have at the time? So for example, it would have like, and then the solutions for all of these things were supervised fine-tuning. So they have like lack of deep domain expertise. So SFT infuses the model with curated high quality data set, making an expert in a narrow field. They also have inconsistent tone and structure. So for example, you could not embed any brand or any kind of tone and kind of personality into the model, or it could be, for example, very bad at JSON formatting. And then SFT would basically help you kind of train and fine tune the model so it would follow these instructions more consistently. And finally, in the way that Google was failing at the time, it would risk factual accuracy, right? So it would hallucinate, and then you could do SFT to ground the model into factual embedded data. So supervised fine-tuning was the bridge from a model that could do anything to a model that could actually do your thing. And that is basically like, those are the advantages of SFT, but the way that you do this is you initialize with a pre-trained model, and you gather and curate data. So you need your representative prompts that are in gold standard responses, ensure covers of tasks, domains, and difficulty levels, and enforce quality controls, duplication, model filtering, bias checks. And then you fine-tune the model. You do supervised fine-tuning, in which you have a train, like a prompt response kind of pairs, and then you evaluate the performance of the final model, and you iterate and refine. So that's how you do SFT. And therefore, as you probably know, our team created something called InstructLab, and it became like a whole thing across the company. InstructLab is basically that loop that I was talking about. You synthesize data, you supervise fine-tune on it, you evaluate, and then you iterate over that. We also have a paper that we released last year called Large-Scale Alignment for Chatbots. And that is the important part, because we were focusing on chatbots. And more recently, we have also released this work in which we have found what are like some of the nuances of supervised fine-tuning small large language models as an InstructLab hub. But then enter the era of agents. So in the era of agents, we go from tell me about X to do X for me, right? So we have a chatbot on the left, but then now we're going to have agentic systems. And agentic systems are these systems that are a lot more autonomous, take decisions by themselves, make long-term planning, and they interact with the world. They can actually change the world. So a chatbot could not do anything but just give you information, whereas an agent can actually change the world via actions. And also the actions are a lot longer. So like an agentic system would take minutes to hours to actually complete a task, which is different from chatbots. So the differences mainly are that chatbots, we're going from chatbots, you have isolated prompt response models, to agentic systems or autonomous multi-turn tool-enabled workflows with complex long horizon tasks. And this means that we need these particular things. We need long horizon planning and reasoning, and we need adaptation and learning from environment feedback. The good thing, and this is where the connection comes from, reinforcement learning is key in these particular settings. And there has been a lot of advances, and I wanted to start with this, in agentic systems in reinforcement learning for agentic systems. Is a very kind of like rapidly evolving field, but it's definitely there. So there's been people that have used reinforcement learning to train models to do better tool integration or tool learning. You provide a language model with tools, and then you basically unroll the model to use the tools. And if it is successful, it just learns to do it better. These can be casted, for example, as you have web navigation, which is a bunch of tools to sense the environment and also take actions in a web browser. And that has also been work that has been done with reinforcement learning. There's also like basically reinforcement learning frameworks to train large language models. And then there's a very recent one in which they train and they create this benchmark that enables reinforcement learning for large language model agents, in particular for like complicated, collaborative reasoning tasks. But then, just to take a step back, what is reinforcement learning? So I'm going to give you a one-slide summary of what it is. In reinforcement learning, you have actions, and you have an agent. In this case, is the mouse, for example, and then your actions are, and then the mouse has to like find the peanut butter in the maze, right? You can take actions there, which is to move in any directions that you can. You have a state, which is the mouse position at any time. You have a policy, which is the probability of taking an action given the state or the position that you're in the maze. You have a transition or the maze dynamics. Basically, if the maze is the environment, there's a transition kind of governance or the rules in which an action affects the environment in a particular way, and then you get a new state. And there's a reward. Depending on the action that you take and the state that you are in, you can get you can basically get a reward, positive or negative or no reward at all. And then the objective of reinforcement learning is to maximize the expected sum of the reward in the trajectory that you take. This usually has like a discount factor as well, so that shorter trajectories are preferred to longer trajectories, but those are details that are not needed currently. And then the important part of this is that RL is meant to harness ongoing interaction and feedback to let agents learn optimal behaviors in dynamic environments. So that was like the idea behind reinforcement learning, and that's why the interactivity part of agentic systems kind of like fits very well together with what reinforcement learning is today. But then, how do you train reinforcement and large language models with reinforcement learning? So first of all, in RL, you learn policies via reward feedback. In a large language model setting, your action is each generated token, right? So every time you're generating a token, that's an action that the LLM is taking. The state in this case is not a maze or the position in the maze, but it's actually the full context. You have all of the tokens that you have generated, plus the tool calling tokens, and then the tool responses tokens. And everything else has to be represented in the context of the model, and that's the state. The policy is the LLM itself. So basically, the LLM is the one that, given the previous history of tokens, is taking the decision to generate a particular token. And then the transition, and this is interesting, is also the LLM, because basically, given the state, you generate an action, and then the transition is what action comes after the state. So basically, the transition is also the LLM, which is kind of something that is not intuitive, at least not to me. But in reinforcement learning for large language models, the environment and the policy are kind of entangled. Unless you have, of course, external actions, like, I don't know, booking a reservation or using a tool in a particular way. Those are actual external environment actions, but that is not always the case. And then you have the reward. Depending on the different rewards that you have, you can categorize all of the kinds of reinforcement learning that you have seen in the last couple of years for language models. So you have human feedback. So you have reinforcement learning for human feedback, which was used mostly for alignment of preferences and safety in large language models. You have AI feedback, which is, for example, using a large language model as a judge to say, hey, this is good, this is bad. And then that's how you can train models as well, instead of human feedback. You have verifiable rewards, which is what people have used to train reasoning models. For example, you verify that the math or the code that you're generating is correct. And then you have process reward models that give rise to PSRL, which is basically you, instead of verifying or give you a reward just at the end of the trajectory, you can also give a reward step by step, and that makes the training a little bit more stable. So given that the challenges that we have in reinforcement learning, the challenges that we have in agentic systems, how do we solve them? So remember that the challenges are both long horizon planning and reasoning, and the other one was interactivity and interactivity mostly. So I'm going to start by explaining how reinforcement learning solves long horizon planning and reasoning. And this comes from, or like the literature or the example that I'm going to use to motivate this is the advances that OpenAI did with O1 in November 2024. So at the time, we saw that O1 was very different from other models because it would make these long traces of reasoning, and they would just show this plot in which you have more test time compute leads to more accuracy and more train time compute as well. And O1 was kind of doing that. It would just like go longer in the amount of tokens that it would take, and that would give it more accuracy. And that also happened with the DeepSeek R1 paper. So in the DeepSeek R1 paper, they used reinforcement learning to train a reasoning model, and that model kind of like gave emergence to this long chain of thought reasoning traces that would lead to like a better reward signals. So that paradigm is called reinforcement learning with verifiable rewards because you can verify the answer, and there has been a lot of work on this in the last couple of months since R1 came. For this, you need verifiable signals. So basically, you need to check that the math is correct or that the code tests pass. And these help because then you cannot do reward hacking. If you had a model that is another neural network, for example, giving you a reward, you would find ways to trick that model into believing that you're doing correct, but then you're actually not doing anything meaningful, and that is called reward hacking. And then there's the big part here is that these reinforcement learning techniques give emergence to this chain of thought solving a la DeepSeek, the same way that DeepSeek R1 and OpenAI did. And the key benefits are that you get deeper, more reliable and aligned agent behavior. And also, reinforcement learning generalizes faster from less data because you're not teaching the model to just predict a particular sequence, but you're teaching the model to just like reach a goal or a target. And the model needs to learn how to get to that target. So it kind of forces the model to learn first principles in a way that SFT doesn't. In SFT, you can just memorize the answer and then just kind of like parrot it out. Whereas in reinforcement learning, you need to actually understand the task structure behind. And then the other part that we need in agentic systems is that we need a model or a system or a method that would be good for adaptation and learning from environment feedback. So I am doing here this comparison again, in which you have SFT that basically just follow the script and then you just memorize to do it. Whereas in RL, you kind of like have to find your own way. So you actually learn first principles, in this case of navigation. You need to understand what is shorter, what is farther, and you need to use that understanding to compute or to do the task in the most efficient way. So in reinforcement learning, you define what you want, but not how to get there. And that is kind of like the beauty behind it. It is also a reward-driven discovery. So agents find novel strategies beyond human demonstrations, as it has happened in both DeepSeek R1, but also in Go and everything. And it's task-specific optimization. So you define success metrics that can happen in your business, whatever you care about. I don't know, you care about customer satisfaction, or you care about, let's say if you are creating a language model that doesn't care about political correctness, then you just define that as your success metrics, and then you just train your agent to do optimal behavior in that setting. And then you have multi-turn crane assignment. So basically in RL, if you have several tool use cases, right, or several environment interactions, reinforcement learning has been created, and there's a lot of techniques to assign credit to what was the tool action that actually helped you reaching the correct answer. And not every algorithm helps with that. And then there's emergent behaviors. So there's self-correction, as you have seen, for example, the backtracking mechanisms of R1, information seeking. Like you can use your tools to go and like find information online, and you can do a strategic planning, which is something that we at least have seen in Cloud Code and other coding agents, that before trying to go and solve the task directly, they make a short plan and then they follow step by step how to do that. And all of those are emergent behaviors from reinforcement learning, because gathering the vast amounts of data that you will need to do this with supervised fine-tuning is unfeasible. And then there's, of course, environment-specific adaptation. Depending on what domain you put the model in, after you train it with reinforcement learning, it kind of like adapts itself to this environment. And that is part of the beauty of reinforcement learning. So let's talk a little bit about what are the engineering challenges of reinforcement learning for large language models. So the policy or the model itself is trained basically with the same infrastructure as supervised fine-tuning, but you need online generation from the model. So for example, you need to use VLLM or SGLang for performance and to do the rollouts. And this is basically generating the sequences, including the tool calls, the interactions with the environment, and at the end, basically to generate the whole sequence of tokens. You need NCCL base or weight update transfer. So you need to transfer the parameters from the policy to the rollouts or the LLM engines. And then depending on the algorithms, you need to host a lot more than just the policy. If you're well, for example, you could have a reference model, which is the initial policy, a value model, which is, for example, a process reward model, or just a value model that tells you how good you are doing in your token generation, a log policy, or something that the policy that actually generates the sequence as opposed to the policy that is being trained at the time, and a reward model, which could be like just a process reward model, or a reward model that is outcome reward model. And then depending on the task and reward, you also need to handle environment interactions. So for example, if you're doing verifiable rewards, you have your whole sequence and you need to pass that sequence to a verifier that tells you if the answer is correct, if it is math, or the test passes, if it is code. And you might also have multi-turn tool calling and tool responses. So you could have a bunch of tools that you're using to solve a problem. Let's say you're in a browser, or you're in or you're like, I don't know, handling a robot. So you need to use tools in order to orchestrate how you interact with the world. And then you need to execute that tool call. So you need like an environment to actually deploy these actions in, and you need to handle that in the infrastructure. So these engineering challenges have been kind of taken care of in a library that we created at the team called asynchronous GRPO, or asynchronous group relative policy optimization. Check the code; it's pretty cool. And yeah, just go take a look. It's pretty fast, and I've tried to make it as simple as possible. It's kind of like a work in progress, but it's been a great experience to just build it.
Although, just one quick question.
Yeah.
If you go back to previous slide, is the policy just the LLM weights or something else?
The policy is the LLM. Yeah. The policy is the policy in reinforcement learning is whatever generates the action given the state. And in LLMs, the actions are the generate tokens. Like you basically generate a next token given whatever tokens you have seen so far. So you're doing a reasoning phrase, or you're basically thinking about how to solve a problem, and then you need to generate another word, let's say. But also, importantly, in agentic systems, the policy also generates tool calling, which is also tokens, but it's like particular tokens that need to interact with the world. So that is like those two things are the actions, but the policy is the language model is the one that is generating these actions. Yeah.
So when we make updates, we are updating the weights, just like we do with SFT.
Yeah. So in SFT, we do gradient steps, right? You have your per data, and then that is actually a very important question. In SFT, you already have your data. You have your, let's say, ground truth input-output examples, and then you train your model to see when you see this input, give me this output, right? So it's imitation, and that's the difference within reinforcement learning. In reinforcement learning, I tell you, look, this is the input, and do something, and I'm gonna basically kind of test you at the end. And if you do right, I'm gonna give you a thumbs up, and if you do wrong, I'm gonna give you a thumbs down. And then you just learn from that. So you don't learn from demonstrations, but you learn by trial and error. So in reinforcement learning, in particular for language models, there's online generation. I give you a prompt, and then I need to prompt the model to actually generate an answer for that. And then I need to verify at the end, which is the verifiable part at the end. Verify that the sequence was correctly generated, and then using that to compute a reward. Does that make sense?
Yeah, I'm just what I'm not clear on is just my lack of understanding. So in SFT, we know that the weights get updated through backprop
Yeah.
and
Same. You also update here with backprop, because it's just that the loss is a little different. So you don't do cross entropy, but you do PPO or GRPO, which are different losses. But at the end, those compute like gradients that you backprop into the model. One important caveat is that you backprop into the model, which is the policy or the actor, but then you need to update the rollouts, which is the VLLM or SGLang actors that you have there in your infrastructure generating responses for your prompts. So actually, that brings me a little bit, like, this is the high-level algorithm of how reinforcement learning works in general for large language models. So you have a bunch of training questions, and because async GRPO is asynchronous, this is what happens. Then you need to generate a bunch of rollouts. So you ask your actor to generate basically answers for the training questions. Then you should generate a lot of different answers for each question, because that's how group relative policy optimization works. Then for each of those sequences or answers, you compute a reward and the advantages. Then you use those rollouts and advantages to compute your reference log probabilities, which is basically the log probability of the model that generated those sequences. And I'm going to go a little bit into the details of why this is the thing. And then you update the policy. So you return the complete samples, which already have the advantages and the generation, to the training loop, which is more of a SFT kind of loop. And in this SFT loop, you compute the backpropagation, you update the weights, and then you transfer those updated weights to the rollout agents, the SGLang agents. So that's how async GRPO works today. It is asynchronous, so it is different from Verl, because it kind of like generates, computes rewards, and trains everything at the same time. Whereas Verl and other training libraries, they first generate, they wait for the whole generation to stop, then they turn off all of the GPUs and put the SFT actor there, they train, and then they do it all over again. So they kind of like have this multi-stage training paradigm. So these kind of like, at the time when we created async GRPO, the cool thing about it is that it kind of, if you tune the number of workers properly, you end up getting, you can get the thing to be faster than Verl on the same infrastructure. So at the time we got, when you have 8 rollouts per sample, async GRPO was a lot faster than Verl and way faster than TRL, which is the Hugging Face repository. I always like to just put Hugging Face that somewhere. The guys, anyway. But yeah, so we managed to like get 40% faster than the state of the art, which was this Verl library, Vulkan something reinforcement learning. And Verl supports a lot more algorithms. So this is not like, I'm not saying that this library is better. Actually, I think Verl is better because they support a lot more algorithms. They're a lot more flexible and they're well maintained. Whereas async GRPO is just kind of a library that we started creating and is just tuned for group relative policy optimization. So this is the architecture of the repository. Basically, you have a policy model, and this is your training nodes. So you shard your model across the different training nodes. You have your generation infrastructure, which is where you create or you do the rollouts, and you have your verification workers. All of this is done via RAID. And then the verification workers are just getting the finalized generations and verifying that the reward is correct. You have your reference infrastructure, which is a bunch of other workers that compute the log probabilities of your sequences, and you coordinate all of that stuff with something called an experienced batcher, which is the one that basically gets the questions from the training nodes, sends the questions to the generation VLLM nodes, and then it gets back the answers and sends them to the reference log probabilities, and then goes back to the training nodes when all of that is done. And then there is a worker dispatcher that is kind of like just managing the initialization of all of the workers in the cluster. And then this is the final kind of like, this is how this algorithm looks in that particular architecture. It's a little too big, so I couldn't put it in a single slide. But basically, the algorithm looks like this. You start with your actor model. You start your LLM engine, which is an asynchronous generation engine. You create n rollouts per question. All of this is happening per question, so it's asynchronous per question. You don't need to wait for anything else to happen. You compute an advantage, and then you compute, and then you send back to the experience batcher. The experience batcher sends them to the reference model to compute the log probabilities. You have, this is a continuous loop that computes log probabilities for anything that gets back, and this asynchronously gets back into the experience batcher. And then as soon as any sample is ready, you send those complete samples to the policy training module, which is just a module that looks very much like the training library. But the difference there is that you are doing GRPO laws. And you do the optimizer step, and then you need to update the weights of both the reference model and the actor models. So this is kind of like the loop that is happening in the asynchronous GRPO library over time. And yeah, and that's it. Thank you so much. If you have any questions, please tell me.
I think this might seem a bit of a dumb question. I didn't know you update reference policy. Is it GRPO specific, or you do it in every other?
So there are different algorithms. GRPO used to have a reference policy, which is just the initial policy, and you're surprised because you don't update that one.
Yeah.
But in DAPO, they removed that. So they don't compute a KL divergence with the reference, with the initial policy anymore. But they still need basically the lag policy. You generate your samples with a particular policy, which is called PyOld here. But then when you're doing gradient optimizations, you do a lot of gradient steps, and those gradient steps not necessarily happen. Well, as you do gradient steps, you're modifying the actor. So you need PyOld and the actor in order to compute a KL divergence between them.
Right.
And that's part of like the GRPO laws as well.
But why did they get rid of it?
Because they found empirically that it doesn't matter. If you remove it, it doesn't
useful divergent.
Yeah, it doesn't diverge.
I think it's a very interesting reason why they removed it. And actually, not just that. It's the other day we were discussing this when you're and we can take this offline if you're interested in it. But there's a very nicely grounded answer to why removing KL divergence is actually a good thing.
Like the clipping?
No, not in favor of clipping, but okay, a bit longer than getting on the board to do the math. When you're the KL is kept there, right? Because you want, typically you run these things with learn reward model, right?
Yeah.
And if you're running with a learn reward model, then KL is there to make sure you're closer to the original policy, because digression can happen.
Oh, because of reward hack.
Reward hacking or otherwise. That reward could be imperfect, and so you're not hacking the reward, but you're just going in a direction that has nothing to do with the
meaningful class,
right?
Yeah.
But then when you switch to verifiable rewards, you don't need the KL divergence because you will not digress.
Right.
Right? So they dropped it, and then you become more sample efficient. And clipping helps, and that's why, remember that we were discussing, why have they have dropped that and increased the clipping,
Yes.
right? So it's like less, it's more free to
They
move.
wanted to diverge more.
But the reason it's more free to move is because the direction is a true direction. I do want to go in the direction of the verifiable reward,
Yeah.
right? So that's the reason why they dropped it.
Makes sense.
Yeah.
You have a couple questions online if you want to unmute yourself.
Yeah.
You don't. Oh, no.
I don't know if I can hear them though.
You should be.
Shrikant or Ishar, do you want to? Oh, here we go.
Yeah. So, with regards to the reward functions here and the reward model, how do we decide which reward model is the right reward model to employ here?
What reward model? Sorry, can you repeat the question?
No, how do we come to a decision of this reward model is the right reward model for the GRPO process implementation?
Well, okay, that's a good question. You need to make sure that when you have, you need to have samples. It's like you have to benchmark the reward model, right? So you have to have ground truth samples that are verified to be, correct, and ground truth samples that are verified to be incorrect. And you need to make sure that your reward model aligns with that. Otherwise, you might have a reward model that is characterizing something that is incorrect when you're doing a reward model. But for example, if you're training verifiable rewards, you don't, well, as long as you make sure that the verifier itself, which is symbolic, like for example, verifying that a mathematical expression is equal to another mathematical expression. As long as you make sure that that thing works, you don't need to benchmark that reward because you just know that symbolically it's going to work. Like, or if you have unit tests, for example, if your reward is passing a unit test, as long as your unit test correspond to the actual goal that you're looking for, if you're trying to solve a bug and you already have a unit test for that, as long as you can just evaluate that that unit test is passing, you know that that's happening, you don't need to evaluate it further than that. Does that make sense?
I think
Yeah.
maybe just to kind of add a little bit more, like how to pick a reward model depends on your task, right? So like if you take an enterprise task, and let's say you're trying to automate an enterprise task, most likely you had some way of verifying success, right? And if you can, so if it's software engineering, it could be unit test, or it could be some part of CI/CD that you already have that is less. So guiding principle should be any reward function that you're leveraging as a tool, it should be cheap to run, and it should be fast, because in a reinforcement learning. I'll give you an example, like in chip design or like engineering, a lot of the verifiers exist, but they are very expensive to actually run. So you can't necessarily run them in loop, right? So what people typically do is they will create a proxy neural surrogate for that expensive reward model. And that's where imperfection comes. There will be always a space for both models. But the guiding principle is that if you already have something through which you are checking your human, when humans are doing work, you're checking and quality control. Try to bring that in. If it is, as Aldo was saying, if it's verifiable, like if it's a deterministic rule, great. If it is not, then, or if it's expensive, then you create a model to approximate it. If you're interested in this domain a little bit more, we do have a project called Reward Hub, where we have been trying to create a library of reward for multiple different tasks. There are things like reward bench, kind of outdated. There's something new that just came up, and I was sending it to GX. It's reward anything bench. It's a new, let's say, a hub for creating general purpose reward models. We have a project by the name of Dr. So, DRSAW, which also is geared towards creating reward function for any task without any training. But yeah, it's an evolving field. Just wanna caveat it.
Yeah, I had a question. This might be a little bit more abstract, I think. But my question was regarding, there's this notion of this difference between reward, which is like the immediate reward you get for taking an action in a particular state, and then the notion of value that, at least from a traditional RL sense, an agent kind of builds an expectation from going into a state, and what's the expected value I can get at the end of an end of work. Like, is there an equivalent notion in RL?
Yeah. So if you look at the literatures, there are value functions directly. Like for example, the new versions of GRPO, there's one called VAPO or VAPO, and in that one they train a value model. What is a value model? Basically, you roll out your policy to solve a task. You get rewards at the end, and then you train the value model, which is another large language model, to just predict the expected reward given whatever sequence you have generated so far, right? So that's basically the classical normal value functions, and they have been used, and they are used in PPO algorithms and in VAPO algorithms. So there are value-based reinforcement learning for large language model algorithms as well. It's just that GRPO dropped that to make the inference more efficient. You don't need to host one other model. But there's also another version of value models which is process reward models. So these are not exactly the same as value functions, because value functions are by construction only meant for a particular task and a particular model. Process reward models, on the other hand, they're more like general. You can actually deploy a process reward model with any other model and get somewhat accurate predictions of how likely the current trajectory is going to give you a high reward at the end. And also process reward models, you can only evaluate them at steps. So you don't do it token by token, but at steps. Whereas value functions, in the more kind of like classical way, you have to be able to evaluate the value function at any state. So basically, at every token or at any partial generated sequence, you can evaluate the value function, but PRMs can only be evaluated at a step, like a step delimiters, basically. Does that make sense?
Yeah, thank you. So I think there was a slide for engineering challenges where you had outlined both value and value model and a reward model. In implementation wise, would this, I think a PRM could potentially fit both the bills. I'm just trying to understand, like, where is there a fundamental difference, or is the value model just dropped?
You're right. A PRM can be, well, if you are using a value model, if you're using PPO, the value model has a particular kind of a role in the algorithm, and you cannot just exchange it for a PRM. You need to change the algorithm a little bit. But conceptually, a PRM is both, as you're saying, a value model and also a reward model. It's just that a reward model is usually considered more like an outcome reward model. So for example, a verifiable reward is an outcome reward model, but also like a normal reward model that you see in the internet, those are usually outcome reward models. So you need to output the whole sequence and then just evaluate the whole sequence. Reward models are usually thought of like that. PRMs are kind of in between, and value models, in the classical way, you need to be able to evaluate them at any partial sequence.
I think maybe it might be a little bit also to think it in a slightly different way as to where GRPO actually comes from, right? So you have PPO as an algorithm, which kind of was the main algorithm, and people used it, and there used to be an explicit notion of what a value function is, and it used to be this model. The one very neat thing about GRPO and the current generation of GRPO style algorithms for RL is that they don't have an explicit notion of a value function at all. And a nice way to think about them, at least the way I think about them, is the following. What are you trying to do? In my mind, you're trying to do this thing. You're trying to do inference time scaling, right? You're taking a model, you're giving it a query, and you're generating 10 answers, right? And we know that, for example, if you choose best of n, that is, in all manner of saying, the upper bound for whatever performance your fancy RL method can get, right? So forget RL for 2 minutes. You're saying, hey, I just did best of n, right? I generated 10 answers, and I picked one, and the model seems to be doing really well. I want to backdrop on that sample, right? The one that was best. So you have multiple ways of doing it. You can do rejection sampling, right? Because technically it is rejection sampling. Or you can, as Aldo was saying, right? You can do it in a single loop where the model generates, you update, you generate, update, right? GRPO is just doing that. GRPO is simply saying, forget value function, fancy math, this and that. What am I really after? What I'm really after is, I did inference time scaling. It gave me a really good answer. I want to do a backdrop and take a step, right? And the neat thing about the math in that case is, when it did do the math, an implicit notion of value occurs, right, to the advantage function. But like,
Right.
I think I just like that notion because you're not trying to retrofit PPO into something or how it transforms. If you're interested in the connection, sure, go do the math, you'll find out there's a value function. But it's much cleaner to just say, hey, I know models become more accurate when I do this. How can I teach the model to do this? Does that make sense? Like especially on value function?
Yeah, no, thank you for that. I think that the exploration of especially the best of n kind of implicitly absorbs the idea of value function.
It also tells you why RL works so well, right? Like what, because we know if we do exploration, we will get better results. I mean, inference time scaling is all the rage, right? It does improve. RL is just a way of saying, well, I'm back rub on it. Right? And GRPO, that's why it's sort of very neat and clean in that sense. I also have been historically a PPO hater, so take that with a pinch of salt.
All right, we have another question online.
Yeah. So assuming we are at the end of the presentation, just from the number of the slide, if I may ask, how do we compare between this this technique, async GRPO, with the Databricks Tau technique, if you have heard of? Because we might face this kind of questions from the customers at the end.
But what was the Databricks Tau technique? I remember I read about it, but I think the Tau technique is a whole. If I'm not incorrect, Tau technique is you do rejection sampling. You basically sample from the model, then you basically verify or get like you classify your samples into good and bad, and then you do direct preference optimization on that. I don't remember exactly correct. I think it does that, but that is different from reinforcement learning because. So I'm gonna assume that it is like that because that's what my brain is telling me now. But this is basically. Excuse me.
I mean, in Tau technique, they do employ a reward model. Yeah.
They employ a reward model, but the reward model, I think, is used semi-online. Basically, you do an epoch of generations,
Yes.
right?
Yeah.
Then you use your reward model to basically give you a reward per sample, and you have several samples per question, basically. And that gives you kind of like these beams of generation per samples, right? And then you can basically rank your answers for each of the questions. And after you have that ranking of answers for each of the questions in the whole data set, you can apply an algorithm that is offline that is called direct preference optimization, which is different than PPO. And the main difference is that here you do a generation of the whole data set, whereas and then you train on that. Whereas in PPO or any reinforcement learning algorithm, you have online generation. So you generate, and at the same time, you do backward propagation as you're generating. So this is what you call an online method, whereas the PO is an offline method. Does that make sense?
Yeah, but end of the day, customer looks at which is cheaper.
So it depends on what you call cheaper. Like reinforcement learning can get you better results, but you need more GPUs to run it, and it can give you better results faster because you're doing online generation and online training, but you need more GPUs to actually run the model. Whereas for DPO, you can do generation and then training, and then you can alternate between these two. So you need less GPUs, and it might be less computationally expensive. And both of them are, I mean, in terms of performance, at least during the last year, although PPO and all of these things are kind of like taking off and kind of being better than the APO now. But at some point during last year, the DPO, direct preference optimization, kind of like matched the performance of the reinforcement learning algorithms, and what is also a lot more simpler to engineer, a lot more stable. It has a lot of advantages. So it's like a simpler algorithm. Yeah. There's a paper called reinforcement learning without tears or something like that, and it's about using DPO instead of reinforcement learning.
Yeah, actually, I'm interested in the client question. Could you provide like more context on what the client is asking in the comparison with the Tau method?
Not yet, but we might face these questions when we start entering into the sales calls, especially when we say the advantages of async GRPO from our instruct lab.
So what Tau does is it causes like test time training. What it does is that it does inference time scaling and try to amortize the inference time cost into the model itself. So it claims to be cheap because it's saying I don't actually do the thinking in the inference time, but I just amortize that into the training time. And there's actually nothing too novel about the method. It proposes something like a generalist reward model And as Otto said, the training process is rejection sampling and then do DPO.
DPO or SFT?
I think it's rejection sampling and then they do some DPO.
That makes sense.
By the way, tau is a
Yeah.
technical block. It's not
Yeah.
a creativity.
Yeah, yeah. But it's
There's
what
like
they
two-
sell. They sell
Two
it.
results.
And
Yeah.
I understand where he's coming from. So in a sales meeting, you're gonna be asked for that because people know about Tao. Tao is just like you can do the same thing that they do in Tao can be done like from Red Hat. It's basically just generating the samples, using the reward model to score all of the samples, and then you just train on the output of those samples. Basically, you can train on the good ones and then not train on the bad ones, and that's gonna give you more or less what Tao is doing. Does that make sense?
Yeah. So I'm just
So-
curious.
Yes.
One last thing. I'm just curious. Like, what if customers say like, I can find a better library than what you have employed for GRPO, and if I do it by myself, what is the necessity of Instruct Lab?
Excuse me? If the customer says, I can find what, sorry?
A better library for GRPO.
That's fine, right? Like, there's a better library. Like, I really like, for example, the Verl library, VERL.
Yeah.
And we can just use that. Like, it's open source, it's well maintained. Yeah. As in GRPO, like, it's a lot more custom to a particular algorithm, whereas Verl has a lot of things that you can do with it. So that's fine. You can always just we can always reuse anything that is open source, and there's no library. The customer is not gonna find a closed source library that is better than Verl for sure, unless they're like OpenAI. But I don't think we're
Yeah.
gonna sell to them.
Yeah. Thanks.
All right.
Any other questions? All right. Thank you again.
Okay.
Otto.
Thank you so much, guys.